Hello, everybody. Welcome to the Big Data Revolution slideshow. So the slides that you are about to see are very text heavy, and I wrote them basically in lieu of there being an official text to read, since there's nothing in the book about this subject. You could just read the slides and be totally fine, but I thought I'd record me reading them just in case you are an auditory learner and you would rather listen to the words and read them at the same time. So I will go ahead and get started. So the big data revolution. What is this? Why is this? Well, so far we've learned about how geospatial data is produced. From our personal use of smartphones, computers, and other personal devices to satellite and aerial imagery we can download onto our computers. We've also examined some of the ways this data is used. There's an important link in this process, however, from data creation to data use that we haven't yet unpacked, and that is where it is stored and how we can access it. But this is more than just a section on data storage. It is a larger discussion about big data with a capital B and a capital D, and the wealth of geospatial data it contains. So in this section, we'll review sources of geospatial data. We'll consider cloud computing and its role in the life cycle of geospatial data. We'll examine big data. What does it mean? How is it used? Who owns it? And why it matters? And we'll discuss big geospatial data and understand how we can use it to harness new discoveries and insights. So, sources of geospatial data. So let's go back to that geospatial data we discussed in Chapter 1. In essence, any data can be considered geospatial in nature if it has a known location. So in a traditional sense, this means things like the location of a road or a building, or the shape of a lake. These are all examples of vector data, otherwise known as points, lines, and polygons that we will get into more in a little later. This also includes satellite and aerial imagery, which is called raster data. Both data types are typically produced through observation, i.e. a surveyor does his or her job, or someone with a GPS unit marks coordinates of observed phenomenon, and physical measurement by a person and analysis/processing on a computer. But this isn't all the data, not even close. What about all that voluntary geographic information, VGI, we learned about in Chapter 1? The location of a Twitter or a Facebook post, the store you purchase your groceries at and use your membership card for discounts and your credit card to buy, the traffic app you use on your smartphone. Each of these actions generates geospatial data. The three examples above are just the tip of the iceberg, but what they represent are the multitude of ways our habits and preferences, both on the individual and group levels, are intimately connected to location. Cloud computing. Okay, this doesn't sound very exciting, but let's talk about cloud computing first. Why? Because this is what has partially enabled the big data revolution. It is also how all the websites and applications we use online and on our smart devices work, which in turn contributes to the amassing of big data in the first place. Those Twitter posts, grocery store purchases, and traffic updates we get are all enabled through cloud computing, which is why it is so important to the big data revolution. Also, cloud computing is something we use all the time and have most definitely relied on heavily in this class. It is how the massive amounts of data, or eponymous big data, is made usable and accessible by the general public for the most part. Cloud computing. It's pretty simple, really. The cloud is basically the internet, making cloud computing information and processing that is transferred via the internet and stored/performed on a remote physical server, as opposed to information that is stored on your personal computer or device or network. So when we do things like geotag a photo on Yelp, post a Twitter/tweet, or shop using a rewards card, the transaction information gets sent via the cloud to a remote physical server. In turn, this physical server stores the data until it is retrieved. So there are three types of cloud computing. You might have used or heard of any of these. SaaS, for example, Microsoft 365 or Dropbox. PaaS, which I'm sorry, I should go back. SaaS means software as service. PaaS means platform as service, and that's an example of which is Salesforce. And IaaS is Rackspace, infrastructure as service. You can see in this graphic here, kind of what those different levels of software of cloud computing are. So those servers we discussed in the last slide do more than just store data. They also do the processing that websites such as these ones listed above require. When you make changes to your Dropbox files, it is the server that is processing the request, and it is the cloud that provides the conduit for information exchange. So a little more on these different platforms. I think these are both very good charts, explanations of how these different platforms and cloud computing sources work. This is explained in the textbook a little bit, actually, so which is part of the reason why I do actually have you read a little bit of the textbook. So I would take a closer look at these when you have a moment. So cloud computing again. Okay, great. But why does it all matter? Because almost everything we do with geospatial data is accessible only via the cloud. There are several exceptions, which we study in a few weeks. But if you look at everything we have done in this class so far, it relies exclusively on cloud computing and will continue to for many other applications. So let's go down that rabbit hole. Where are these physical servers our cloud sends our data to? It's really about unlocking the enigma that is the internet itself. Here are some interesting resources for getting a grip on the physical internet that provides our seemingly invisible services. I'm not going to go over these, but you can actually go in and click on these links and see some of this stuff. I find all this stuff incredibly fascinating, and if you're into geography at all, I think or the technology or the internet, you should take a look at these. So now let's get to big data. Big data are data sets that are so big they cannot be handled efficiently by common database management systems. Dasgupta, 2013. It seems so intangible. I guess that's because it is, quite literally. Check out the infographic on the right to get an idea of how much data is generated every minute. This is for 2017. The amount of data produced grows exponentially each year, and the only place to store it is on these large physical servers. And what about the size of these servers? Just to give you some idea, quote, Google holds somewhere around 10 to 15 exabytes of data. An exabyte equals 1 million terabytes. If a personal computer holds around 500 gigs, that would mean 1 exabyte would equal 2 million personal computers. And Google's 15 exabytes would be around 30 million personal computers. Phew. So now the Dasgupta quote above makes a little more sense, right? As to where the data comes from, we can see examples on the right. Anything that involves hundreds of thousands to millions of users creating unique data inputs via applications that involve the cloud. Even just using your computer to access the internet creates a known piece of data, i.e., at this IP address you log onto a browser and surf the internet for 10 minutes. But what else? To get to the bottom of it a little more, these were some of the burning questions. Big data burning questions. So what does big data look like in a raw form? I ask this question because in GIS, data is in a table, a spreadsheet if you will. All that information that the maps and images we have used in the assignments have their meaningful data in a table, also known as an attribute table, which is also somewhere on the internet. Could we theoretically print the world's largest spreadsheet with all the big data? Predictably, the answer is no. Big data is all code. It doesn't make any sense. If you were to pop the hypothetical hood of the internet, you would see a sea of data that has no meaning, or an engine that looks like a lake, to extend the metaphor, which of course still makes no sense at all. So if it doesn't make sense, how is it made usable? So have you ever heard of data mining? This is where it comes into play. However, this mining is not done by a human, but by computers and artificial intelligence. The humans will write the pattern recognition algorithms that will tell the computer/AI what to forage for, and they will produce information that is then recognizable to the analyst. The key here is that there is no narrative with big data. We have to go in and look for the patterns on our own. So who owns it? Well, whoever's product you're using, generally speaking. We have already learned that all satellite imagery and data is owned by someone. What about cell phone call records? These are owned by your cell phone provider, just as Facebook owns its own data, as is the information on your iPhone is protected by Apple, etc. Of course, not all data is proprietarial. For instance, the information we can access through ArcMap and ASRI, the map-making software we'll use in a few weeks, is all public domain, so to speak. Why is big data so important? Well, from a general perspective, the continued amassing and analysis of big data will hone insights into a variety of human and technical processes. See this summary on the SAS website, leading to overall efficiency improvements in a variety of sectors. The geospatial realm is no exception. For all the amazing hardware and tools we have to understand geographic phenomena, access to big data allows the user to fashion deeper insights with contemporary mapping tools, which leads us to big geospatial data. We finally arrived at big geospatial data. Knowing what we do about cloud computing and the different kinds of platforms it involves, and a bit more about big data in general, let's drill down into how big data and geospatial data intersect. Sources of spatial big data include GPS, GPS-enabled devices, satellite remote sensing, aerial surveying, radar, LiDAR, sensor networks, digital cameras, location readings of RFID. I've referenced this person, Dasgupta, here a number of times throughout the text. You'll see the references at the bottom. So when we talk about big spatial data, there are 5 V's that kind of help put a container around what it means. So the first V is volume. There's so much of it, right? Satellite imagery covers the globe and is so vast. And all that imagery that satellites produce isn't just a static picture. Each and every raster, the basic component of an image, has lots of data within it. So you can imagine just one picture creates, vast amounts of information. Sensors are expanding worldwide at a rapid rate, and what we mean by sensors is, the first thing that comes to mind is the Internet of Things. If you've heard of, putting the internet technology in your Google Home, stuff like that, those are all sensors that are all adding information to the cloud. And digital cameras have reached several billion through spatially referenced cell phones. The next V is variety. So the form of data is based on 2-dimensional or 3-dimensional points configured as vector or raster imagery, points, lines, or polygons, or images. This is entirely different than conventional big data, which is alphanumeric or pixel-based. So this means there's a lot of different forms of this data. We can get sort of flat images, we can get 3-dimensional images, and we can do a lot with it. So the third V is velocity. Velocity, it's very fast since imagery travels at the speed of light. So we've got this sort of instant connection with the imagery and the data that's produced. The fourth is, make that go away, veracity, which means its quality or its truth. For vector data, points, lines, and polygons, the quality varies. It depends on whether the points have been GPS determined or determined by unknown origins or manually. Also, resolution and projection issues can alter veracity. For geocoded points, there may be errors in the address tables and the point location algorithms associated with addresses. For raster data, veracity depends on accuracy of recording instruments and satellites or aerial devices and on timeliness. So the section on veracity is more just to say that there are ways that the data can have errors in it, but there are also ways we can clean it up. And the fifth V is value. So for real-time spatial big data, decisions can be enhanced through visualization of dynamic change in such spatial phenomenon as climate, traffic, social media-based attitudes, and massive inventory locations. So think about, again, social media stuff that's happening in real time. We can map that actually as it happens. And when you think about how Amazon works, it's all based upon having a inventory that can be accessed with a location on this cloud computing system instantaneously. Exploration of data trends can include spatial proximities and relationships. And once spatial big data are structured, formal spatial analytics can be applied, such as spatial autocorrelation, overlays, buffering, spatial cluster techniques, and location quotients. Spatial big data analytics. Taubeler's first law of geography. I think we've come across that before, but it states that everything is related to everything else, but near things are more related than distant things. So this is just something to bear in mind as you start thinking about how and why we can use big spatial data. There's power in location. Location targeting improves the performance of mobile advertising, and a lot of other things that we'll actually get into in the next couple weeks. And grand challenges such as sustainability and climate change, health, transnationally organized crime, or the fighting of, energy, economic development, etc. For example, eco-routing rather than faster routing. Data-driven real-time science. New types of geospatial data generated continuously at a very high speed. You need to look at the incoming data on the fly and make decisions in real time. So this means that there is a need within big geospatial data analytics to have people on the ground looking this over, which is a complex process in and of itself. But in order to make the veracity of the data, as we already discussed, as good as possible. Data-intensive hypothesis generation. This is just a fancy way of saying looking at the data and coming up with questions that it makes you think to ask. So by looking at spatial statistics, machine learning, spatial data mining, and geovisual analytics, and A/B testing. Spatial big data platforms, other examples, that would be geo-targeted event observation, GeoViewer, for real-time situation awareness for incident commanders and decision makers during disaster events. So these are some charts you can look at, or some graphics of how a few different studies have used big geospatial data to track the movement of taxicabs based on space-time and attributes. It's very interesting. And this takes it to another level, shows you some other sort of mapping and plotting you can do with it. And this is all something you can do in GIS or ArcMap or ArcGIS Online. So what are some applications of spatial big data and analytics? Politics, supply chain management, public safety, urban traffic, emergency management, healthcare, energy, climate science, marketing and advertising. There are so many ways it can be used. So in summary, tying together big data, analytics, and GIS. A technical, algorithmic, and software base of the intersection of big data, analytics, and GIS has been set. Since the preponderance of data is or can be georeferenced, the size of big spatial data is vast. Analytics are needed since the extent of map visualization is overwhelming. Computer science and GIS science are taking the lead in this. The limited documented examples illustrate the power and discovery aspects, and there are lots of questions and much future work to be done. So those are my sources for those slides. The ending note here, just to reemphasize that this is absolutely a burgeoning field, and if you are at all interested in coding, artificial intelligence, or even just learning a tiny bit so that you can actually ask some big questions of this big data, there's a lot of stuff out there. And there's a documentary you're watching this week that I think will help drive this home. So I hope that was helpful, and enjoy the rest of your assignment and have a great day.